Hello dear students, welcome to Organic Chemistry classroom. Today we are going to talk about the heterocyclic compound pyrimidine. Pyrimidines and purines are the two families of nitrogenous bases that make up nucleic acids. In other words, they are building blocks of DNA and RNA. Each DNA strand has a backbone that is made up of sugar and phosphate chain. Attached to each one of these sugars is a nitrogenous base that is composed of carbon and nitrogen rings. The number of rings present in this base determines whether the base is a purine two-ring system or a pyrimidine one-ring system. The purines on one strand of DNA form hydrogen bonds with the corresponding pyrimidines on the opposite strand of DNA and vice versa, and this holds the two strands together. This is the most important function of purines and pyrimidines in DNA molecules and is known as a base pairing. Because of hydrogen bonds are not as strong as covalent bonds, base pairings can easily be separated, allowing for replication and transcription. Purines also always bind with pyrimidines through complementary pairing. The ratio of the two will always be constant within a DNA molecule. In other words, one strand of DNA will always be an exact complement of the other as far as purines and pyrimidines are concerned. This phenomenon is known as Chergav's rule, named after Erwin Chergav, who first noticed it. This complementary pairing occurs because of the respective sizes of the bases and because of the kinds of hydrogen bonds that are possible between them. They pair more favorably with bases with which they can have the maximum amount of hydrogen bonds. They are, there are two main types of purines, adenine and guanine. Both of these occur in both DNA and RNA. There are three main types of pyrimidines. However, only one of them exists in both DNA and RNA, that is cytosine. The other two are uracil, which is RNA exclusive, and thymine, which is DNA exclusive. Adenine pairs with thymine with two hydrogen bonds. Guanine pairs with cytosine with three hydrogen bonds. These specific pairings also factor into Chargaff's rule. The number of adenines in a DNA molecule will always be equal to the number of thymines. The same goes for guanines and cytosines. The purines, that is adenine and guanine, have a two-ringed structure consisting of a 9-membered molecule with 4 nitrogen atoms. The pyrimidines, cytosine, uracil, and thymine bases only have one single ring, which has just 6 members and 2 nitrogen atoms. Pyrimidine is a six-membered heterocyclic ring compound containing two nitrogen atoms at 1,3 positions, that is, meta positions. Its structure is represented here. The pyrimidine nucleus occurs in many natural products such as nucleic acids and also in synthetic drugs such as barbiturates. Pyrimidine is a dibasic compound. Three pyrimidine bases are components of nucleic acids. They are cytosine, uracil, and thymine. They exist in two tautomeric forms. Only the latter forms can be ribosylated to give the nucleosides. Pyrimidine ring is comprised also in the structure of thiamine and barbituric acid. These are the resonance structures of pyrimidine. First one for N1 and the second one is for N3. Pyrimidine shows aromatic properties because of the resulting molecular orbital satisfies the Huckel's rule, that is 4n plus 2 rule. The nitrogen lone pair is not released into the aromatic system because it is perpendicular to the pi system. The nitrogen withdraws electrons by resonance, resulting in an electron deficient ring system. Let us discuss the preparation of pyrimidines. First one from alkyl pyrimidines. Alkyl pyrimidines on oxidation followed by decarboxylation gives pyrimidine. Second one from chloropyrimidines. Catalytic reductive dechlorination of 2,4-dichloropyrimidine gives pyrimidine. Third one from barbituric acid. Pyrimidine may be prepared from barbituric acid. Barbituric acid can be obtained by the condensation of malonic ester and urea. The product barbituric acid, that is malonyl urea, on reaction with phosphorus oxychloride POCl3 followed by reduction with zinc dust gives pyrimidine. Moving on to the characteristic reactions of pyrimidine. Pyrimidine is a weaker base than pyridine because of electron withdrawing effect of the second nitrogen atom present in pyrimidine. Pyrimidine gets protonated in acidic medium. Presence of electron donating groups like alkyl alkoxy enhance the basicity. Electrophilic substitution reactions also occur in pyrimidine. Pyrimidine is less reactive than pyridine due to two electron withdrawing groups towards electrophilic substitution. However, presence of electron donating groups on ring, electrophilic substitution is possible at fifth position, the least electron deficient position. These are the electrophilic substitution products. Bromination gives 5-bromopyrimidine, nitration gives 5-nitropyrimidine, sulfonation product is pyrimidine 5-sulfonic acid. These are the reactions of substituted pyrimidines: nitration, sulfonation, bromination, formylation, that is CHO insertion, and azo coupling NN bond formation reaction have been observed with substituted pyrimidines. Nucleophilic substitution. Pyrimidine easily undergoes nucleophilic substitution. Nucleophilic attack takes place at 2, 4 or 6th position. Thank you all for patient listening.